Thank you. So before I begin, let me give some background on malaria and Medicines for Malaria Venture. Malaria is a life-threatening disease that's caused by 4 Plasmodium parasites. The disease is transmitted exclusively through bites by the Anopheles mosquito. After being bitten, symptoms begin to appear, usually in 8 to 25 days. Initially, symptoms may be flu-like, but then the person develops further symptoms, which include moderate to severe shaking chills, high fever, profuse sweating as the body temperature falls, headache, vomiting, diarrhea. And malaria is prevalent in tropical and subtropical regions around the world. Well, 150 to 250 years ago, malaria was endemic across every continent in the world. In fact, in the U.S., one of the drivers to move west was to get away from the malaria that was on the East Coast. Today, malaria is mainly prevalent in the tropical and subtropical regions of the world, such as Africa. So in those regions, about 3.3 billion people are at risk, which is approximately 50% of the world population. There's 247 million cases of malaria reported each year, and about 1 million deaths reported each year from malaria. 91% of the deaths happen in Africa, and 85% of the deaths are in children under 5. And malaria is gaining resistance against all traditional treatments for the disease. So malaria is transmitted, as I said, by the female Anopheles mosquito. And when an uninfected mosquito bites a person with malaria, the malaria virus is taken up in the blood from the person being bitten. The virus matures in the mosquito's gut and forms sporozoites, and when the infected mosquito bites an uninfected person, the sporozoites are injected into the person's bloodstream. The malaria sporozoites travel to the person's liver, where they infect the person's liver cells. And in the liver cells, sporozoites multiply into merozoites, which rupture the liver cells and spread into the bloodstream. There they infect the red blood cells and multiply and burst the cells to infect more red blood cells, and the infection cycle continues. If a person is bitten by a mosquito, the malaria virus is taken up by that new mosquito, and the transmission process continues to find a new victim. Since red blood cells don't have DNA, when malaria is infected at the red blood cell and a malaria-infected red blood cell is treated with a DNA stain, you can detect the malarial DNA in the cell, as can be seen in this picture. Well, from 1975 to 1999, 1,393 drugs were introduced by pharmaceutical companies. 13 of the drugs, which is less than 1%, were for neglected diseases, and only 4 were for malaria, which is less than 0.3% of the drugs that were being developed. Over the year, as I mentioned, malaria has gained significant resistance to all known treatments, and so in 1999, a group from the World Health Organization formed Medicines for Malaria Ventures to address these issues. The mission of Medicines for Malaria Venture is to reduce the burden of malaria in disease-endemic countries by discovering, developing, and facilitating delivery of new, effective, and affordable antimalarial drugs. And the vision is a world in which these innovative medicines will cure and protect the vulnerable and underserved population at risk of malaria and help to ultimately eradicate this terrible disease. Well, when Medicines for Malaria Venture started in 1999, there were no compounds in their portfolio and there are no projects they are working on. And in 2009, they celebrated their 10th anniversary. And in 2009, the portfolio included 42 programs against malaria, with 4 compounds in phase 3 clinical trials and 3 compounds in registrations. And these develops have been funded solely by the Medicines for Malaria Venture, and over the past 10 years, they built up a pipeline of drugs to combat malaria. So in 2013, 4 years later, the portfolio has continued to grow, with many new concepts moving forward from translational research. In addition, since 2009, 6 drugs have been approved for treating malaria. This graph shows the data from the previous 2 slides, and what it shows over the past 4 years how Medicine for Malaria Venture effort has really taken off. And you can see that there's been tremendous growth in the area of translational research. So the DNA sequence of the human malaria parasite was reported by Gardner et al. In Nature in 2002. And since that time, current approaches to discover novel chemotypes involved mining the malaria genome, elucidation of known biochemical pathways, and using high-throughput screening techniques. The high-throughput screening assay for human malaria parasite is grown in 1536 well microplates. The screen is imaging-based and is a stage-specific assay using DNA-specific dyes. And using this assay, they can achieve a 0.5 to 1% hit rate when they're doing a screen. And using this assay, several novel anti-malaria chemotypes have been identified. One screen, which was performed at St. Jude Children's Research Hospital, identified several chemical series of interest, which were further validated. One series, a 1,2,3,4 tetrahydroisoquinoline 1-ones, which is the compound on the right labeled number 1, has progressed to the lead optimization stage. And studies identified that molecules where the carboxylic acid 2, which is on the right in the lower right-hand side, was a key intermediate. And so what was needed was an efficient method to synthesize and resolve a racemic mixture of compound 2. And so medicines, malaria, and Freeslate worked together to identify a way to do this. The work that we did to support the collaboration was done using Freeslate's reaction screening workflow. Using the reaction screening system, you can screen hundreds of reactions per day using a variety of conditions. The system is based on our core module 3 robotic platform. And going from left to right, the system has the following deck elements. You can see on the far left-hand side a balance, followed by a PDT rack, a 3-position vortexer, a combination solid dispense hopper and tool rack, 2 heated cool stir bays, a capping station, a washing station, and then it has some ARM elements, which include a multifunction powder dispenser, a valve plate gripper, a 4-channel heated dispense probe, and single-channel dispense probe. The system can perform standard organic transformations and is ideal for route scouting and screening and process development and optimization applications. Our speaker today is Dr. Poo Sun. Dr. Sun is a senior research scientist at Freeslate, where he works in managed services group for small molecules. His group provides high-throughput screening services to pharmaceutical and biotechnology customers, including optimization and organic transformations. Dr. Sun received his BA degree in chemistry from Hanover College and a PhD degree in organic chemistry from Penn State University under the tutelage of Professor Stephen Weinrib. His graduate research focused on natural product synthesis. The title of Poo's presentation today is Advancing a Therapeutic for Treating Malaria by Identifying a Challenging Diastereomeric Salt for Chiral Resolution using High-Throughput Screening Research.
Thank you, Dave. So the title of today's talk is Leveraging the Power of High-Throughput Screening to Identify a Diastereomeric Salt for Chiral Resolution. This work is the result of a collaboration between Freeslate, Rutgers University, and MMV. As Dave has stated earlier, MMV is a nonprofit organization that, with the mission to discover, deliver, and new affordable antimalarial drugs. For the compound we're talking about today is actually come from one of their programs. A 4-step synthesis was developed to prepare this key chiral and enantial intermediate. And out of this 2 steps for chiral resolution purpose, which I will show you on the next slide. For the chiral separation itself, chiral preparative supercritical fluid chromatography was employed for the separation. They did some assessment to see if iterative manual classic chiral resolution can be employed to for scale-up for separation, so we really don't have to do this 2-step synthesis, but it was proven challenging. So MMV and Freeslate agreed to collaborate so they can utilize our high-throughput chemical development workflow to see if it's possible to find a diastereomeric salt to separate these 2 enantiomers. As I stated, so this slide is to show you what MMV's effort so far. For a relatively large scale for them to get enough compound, it's what's shown on top. So what you see here is the first structure is what you have seen so far is this Racemic 2. Two-step, fairly facile synthesis to synthesize this Racemic carboxylic acid 2. But to get a pure enantiomer out, which you see on the right, you have +2 and -2. +2 is what's desired. And they esterification and hydrolysis was used for this purpose. So the way they did it is to make the methyl ester first, followed by supercritical fluid, supercritical fluid separation, followed by hydrolysis with using lithium hydroxide with water, methanol and water. The separation is actually fairly efficient. You get a very good recovery and really good EE, but we do need to use two synthetic steps to achieve this. And for chiral resolution, our classic chiral resolution, they attempt a couple different things, and they did notice amino alcohol was definitely the most promising chiral amines to use. For this particular experiment, they used this trans-amino indinol, one equivalent of it, using 1:1 propylnitrile MTBE mixture to try to achieve the separation. As people will know, for a classic chiral resolution, you're forming from an enantiomeric pair using one chiral amine to form two diastereomeric salts. And then you're trying to find this solvent system which will differentiate the solubility difference between these two diastereomeric salts. So for this particular effort, and also really the desired one in this case is +2, you would like that diastereomeric salt to be solid, to be less soluble. So in effect, what you want to do is to form the salt, and the solubility difference, hopefully the undesired one will be more soluble, wash it away with this solvent, and the what you want is more enriched as solid. But this particular effort, and I think that at the end what they did is use acetic acid and aqueous solution with acetate to extract to bring back the carboxylic acid. The effort was, the yield was good, but the recovery yield is fairly low at this point. So it's really not good to be used for a bigger scale. With this in mind, so what we did is we look at what have been done at MMV and think the way we plan our first screening is to see, okay, chiral amino alcohol is the most promising one. So in effect, we were actually doing a fairly focused screening already. So all the 8 chiral amines are amino alcohols, including the hit amino indinol and a couple other amino alcohol they have studied. And then we also picked 12 different solvent mixtures. Since we really don't have a lot of understanding of solubilities in terms of all this diastereomeric salt that will be formed, so we employ a range of solvent and solvent mixtures. You will see on the upper right of this, the first one we picked obviously is the solvent system they employed, the propylnitrile MTBE mixture. But the remaining 11, we have a range of solvent. They're fairly typical solvent for resolution purpose. Since we really don't know a lot about what we're going to see, so we, for example, for acetone, we not only use the pure acetone itself without the solubility by adding some water or mix with heptane just to have a range of polarity in terms of solvent. As you can see, we use methanol water mixture, IPA water mixture, THF water mixture, acetonitrile. All this is just to have a general understanding of what we're going to see. As you can see on the lower left, the library layout is we have 8 rows of chiral amino alcohol and 12 columns of solvent mixtures. For the condition, for the experimental conditions, we employ 1-to-1 ratio of Racemic 2 and chiral amino alcohols, and we have about 32.5 mg of this Racemic 2 per well. And as we'll show you on the next slide our overall workflow, but here is just some conditions. We use methanol for all wells for salt formation step because you have to form the salt first, and then the solvent mixture you show on the upper right, we use the 500 microliter. So we have the concentration of about 65 mg per mil. So here, as you can see, is about a 3-day operation. The first day is about salt formation. So the thing we want to do first is from Racemic 2, combine with chiral amino alcohol to form 2-diastereomeric salt. The way we would like to encourage that is to use methanol to do this work. So we have better solubility, and we have done that using 45 C within 2 hours. After this operation is done, we just remove the methanol so we can introduce the resolving solvents. That's done on the second day. So after it's dry, and then we add 500 microliters of each solvent mixtures, depends on the library design, to each well. And then we'll seal the plate and run the temperature profile on the right. As you can see on this graph, is we start with about 50 C and gradually dropping on to 10 C. With stirring for the bulk of it, and then non-stirring at the very end, just to settle the whole solid. So after the second day, so in a way, what we're doing here is we're trying to study the solubility difference between the 2-diastereomeric salt form. So after this second day, what we employ to use our filter assembly. So we have all the plates are sealed at this point. We actually did a centrifuge first, so to compact any remaining solid, if any, and then we'll use this 4-tip assembly to transfer supernatant on top to a dilution, HPLC dilution plate, because they tend to be too concentrated for LC analysis. And through appropriate dilution, so the LC plate is ready for analysis. But we actually do not analyze the whole plate. So after this operation is done, we get the LC plate prepared. What we'll do next is to open up the master plate where all the experiment has been done so far, and we'll do a visual observation. So what we want to see here is to see solid. Solid means there is something not being dissolved. Hopefully, is the +2. That's hope. And if you see fully dissolved wells, that means both diastereomeric salt has been fully dissolved, so there will be no resolution. So no point doing the analysis in that particular well. So as you can see here is we only do Chiral HPLC on the certain wells with solid present. Here, I would like to just briefly show you our Chiral HPLC method. Typically, with any kind of a high throughput, doesn't even have to be chiral resolution screening. We would like to typically there's some method available already for analysis. We always try that method, to see what that method is and see if there's possibility to reduce the length of the analysis if possible. For chiral resolution, sometimes it's hard because it's just typically a harder separation to do. But the general theme is still the same, is to see if HPL analysis can be, a shorter HPLC analysis can be employed for this purpose, because for high throughput screening, every minute you save can be amplified 96 times in this case. So we would like to have some method that will last about overnight, and so we will have the results the next day. So this is the results from the first plate on the left. And we also try to compare with some previous bench top work MMV have done. So as you see, what's marked on red is we see many fully dissolved wells, which is not a good thing because there's no hope of a resolution if you see fully dissolved wells. So that's not a good sign for now. And also for wells that have solid, which there's hope of resolution, a lot of them do not have resolution, so you do see kind of equal amount of +2 and -2 in both the supernatant and the solid form. So we do get one hit. As you can see here, is we use this RR version of this trans-amino indole. And what we see here is a +2 salt is concentrated in solution, which is not desirable at this point because we want the +2 to be concentrated as solid, wash away the -2 diastereomeric salt. The solvent is acetate, and we use one equivalent of this amino alcohol. As you can see, the yield, both the yield and E just okay, and if you calculate the solid based on the supernatant, is really not that great. And this is some MMV work, which kind of I showed you earlier, but there's some new information here as well, is to just look at the detail here is they use 1S, 2S trans-amino indole. What they do see is +2 salt is concentrated in solid, which makes sense. It's the reverse of what we have done. We use R and R. And their yield and their EE is better, and because this is before crystallization. What I've shown you earlier is after crystallization, after a release of the carboxylic acid 2 with acetic acid. But they also use one equivalent of amino alcohol. But on their other studies, what they have seen, they have also seen that maybe they're actually forming a 2-to-1 amino alcohol acid salt. So you might actually need 2 equivalent of this amino indole for it to fully form the salt. So what do we see here? So what we see here is out of the 8 amino alcohols we have tried, only this structurally constrained amino alcohol is actually the hit, which in a way, because it's definitely the unique structure out of the 8, so okay, that makes sense. It's different from other ones. And the poor, so we do observe this poor resolution and mass recovery. So what might be the reason for this? First of all, what we do see here is a lot of fully dissolved wells. So that means even though we're trying to employ a range of solvents for this study, for 12, we picked 12. Maybe even with that, we really do not have the polarity of the solvent system we pick is still too much solubility involved. So we need to even lower the solubility even further for us to even have a chance of a hit. And also what we mentioned here is 2-to-1 amino alcohol, 2-to-1 amino indole, and this carboxylic acid salt formation. For the first screening, we only use one equivalent. That might not be enough. So if 2-to-1 is formed, so that means that a lot of free Racemic 2 was floating around because you run out of this amino indole to form salt with. That is readily dissolved. So that means there will be no resolution for the ones that have now formed the salt. So with all this concept in mind, our idea here is to see test for, so our structurally constrained amino alcohol is the hit we're going to focus on. So we want to answer a couple questions. Is trans necessary? And we want to test both the 2 equivalent and 1 equivalent. And we actually would like to intentionally lower the solubility of everything we test because there are too much the solubility here. So for the next slide, as you can see here, it's not a full, typically we do 8x12, 96-well screening, but for this one it's fairly focused. We only employ the first 4 rows. So within this, there are 3 variables we mentioned: solvents, the 4 chiral amino indenols, and the equivalents. So what we have done here is, as you can see on the upper left, you will see ethyl acetate as our hit, and we want to employ a lot of different solvents. But what we want to use is any solvent we employ, we add equivalent amount of haptane. And a lot of time you have to be aware of what's miscible with haptane. So certain solvents are not miscible. For example, acetonitrile is really not miscible with haptane, so we didn't really use that one. For example, for number 5, we use propylnitrile because they're barely miscible. You have to kind of really vortex it for a while for it to mix, but they're mixable at the end. But so the whole purpose of this is to, whatever the solvent system you're going to look at, we learned from the first screening we want to lower the solubility even further, employing this haptane as our modifier. As you can see, the screening itself is very similar to the first one, but if you see the library layout at the end, you have 4 amino indenols as 4 rows and 2-to-1 ratio of this chiral amine and a 2 ratio. And 1-to-1 is the last 3 columns. And the whole experimental condition is very similar to the first one. It's a 500 microliter methanol to form the salt and 500 microliters of solvent mixture for the resolution purpose alone. Okay, so I'm not going to go through the workflow again because the workflow are the same as the first one. This is just some raw data coming out of from this particular screen. So a lot of things kind of shown is, first of all, the cis really didn't work well for row C and row D, and the 1-to-1 ratio, as we have seen before, really just don't have enough. So all the thing I've seen so far is 2-to-1 ratio is needed to form this salt, and which will have a better resolution. And propylnitrile and the haptane mixture, which we highlighted here, we're going to go into the data a lot more. But here is what we see: both the R and R and SS have a really good resolution as we anticipated, and with a reversed solubility. So here's our observation. Only what I have said earlier on the previous slide is the trans amino indeno is needed for this Racemic 2. If you take a look at the structure, we really, even at this point, we really don't have a crystal structure for this 2-to-1 compound form. But in a way, it kind of makes sense. You know, this carboxylic acid 2 itself is trans, and what we needed is trans as well. But why 2-to-1? We really have to kind of see the structure to know. And what we have seen here so far is 1-to-1 propylnitrile and the haptane is definitely the best solvent mixture. As you can see here, For well A5, which is definitely the hit with +2 as the solid. We'll see a solubility of a -2 salt is fairly high, 27.5 mg per ml, with approximately 0.03 mg per ml +2 salt. In a way, you see they're actually about this 100-fold solubility difference, which is fairly significant between these two diastereomeric salt formed. As you can see here, this is the Chiral HPLC we're seeing for this particular well. So what we want to see here is, before I get to the scale up that MMV have attempted, which is different from any of the condition we have tried within the screening itself. And let's take a look at, think about what we have seen here, well A5 a little bit more. So if we look at the screening condition here is, we have 32.5 mg of this Racemic 2. So you split in half, you have about 16.25 mg of each enantiomers. So the whole point here for the first section of this slide is we have about 32.5 mg of each isomers. As you can imagine, before we think about anything is think about what's the most ideal situation, which hopefully it doesn't achieve that often, is we can dissolve 32.5 mg of -2 salt with 32.5 mg of per ml of +2 salt, barely soluble. That's the most ideal situation. That means we have the best resolution. But so what do we see here within our screening? Our screening for the middle section of this slide, what we see here is we see 27.5 mg of -2 salt solubility with about fairly a small amount of +2 salt dissolved. And for the calculation, if you reverse the calculation, this is what you see for the supernatant. If you see the solid part, you still calculate there's still about 2.5 mg of -2 in the solid, which we know will ruin the EE part. And most of the +2 is still with the solid. So our conclusion here from our screening so far, we really have a good hit, because we really find a condition where we can really differentiate the solubility difference between these two diastereomers. But the poor EE come from the fact that because we use 500 microliter of this solvent mixture, somehow will distinguish the solubility. But we really don't have enough to dissolve all the -2 present in that particular well. 2.5 still was not dissolved, remaining solid, ruin the EE for that well. So after we do this analysis, the conclusion is fairly obvious. So what do we need to do is we need to use more for any scale up. What we need to do more is we need to make sure we have enough of this propionitrile heptane mixture to dissolve all the 2-to-1 amino-indinol -2 salt. Because the more you use, so the problem, typically the problem is the more solvent you use, you not only dissolve the one you want to dissolve, in this case is -2 salt, you also dissolve the one you want to keep, which is +2 salt. Because of what we see here is this dramatic solubility difference, the trade-off is really minor. The more solvent, you really use a lot of solvents, but amount of +2 salt loss with this trade-off is really minute. Is really is okay, and also we get a much better EE as well with this more solvent. So here's the scale up of what you can. So in this particular case, this is work done by MMV and Rutgers University. So after we have discussed the result with them, so we come out with scale-up protocol here, which is slightly different, definitely different from exact condition we see in A5, which I have just described earlier. So for this particular scale-up, they use 16.4 gram of this Racemic 2, and use 2 equivalent of this SS trans amino indinol, and suspended in 500 mils of this 1-to-1 propionitrile heptane mixture in reflux for 3.5 hours. In this particular case, first thing we observe here is we actually did not use, for the scale-up, which is good, is we did not really use a methanol salt formation step. That step is for screening only, because that particular step for screening is we want to ensure under any kind of condition we have a better solubility. That's why methanol is employed. Here, we just use reflux to achieve that, to achieve the salt formation. So as we discussed in the earlier slide, we have 500 micromils of this mixture. To achieve 27, so we want to dissolve all the -2 salt, plus, in this case, plus more, because we want to make sure -2 salt is fully dissolved in this case. So the minimum amount of solvent we need to achieve that is 300 microliter. And we, for the scale-up done in Rutgers University, 500 ml is used, just to ensure all -2 salt is readily dissolved in this particular experiment. And another thing they observed is because the +2 salt, typically when we do this kind of operation, a lot of time when you do the reflux, everything go into solution, and then when you cool it down slowly, the thing you want to come out. But in this particular case, because the solubility difference is so dramatic, even under reflux, what they have observed is still a slurry. So pretty much after the +2 salt is formed, it immediately crash out. Most of them never redissolve into the solution, even under reflux condition. So even under reflux, what you see is still a slurry. So, so this is all good. So after it cooled to room temperature, the thing is the solid, which mostly is hopefully +2, is filtered. And we further, because there still might be some -2 lingering around because the solvent is not completely dry. So more additional, this 1-to-1 acetonitrile heptane mixture was used to wash the solid, to wash off any lingering -2 salt. In this case already, what we'll see here is at this stage, the salt is still being formed. We see 94% recovery with 99.3 EE. And the first step is taken to free the acid, which is what we want. That's very similar to what they have done before, is to use acetic acid aqueous solution followed by ethyl acetate extraction. After that work, what we have seen here is 85% yield of the pure +2 carboxylic acid, not a salt anymore, with still the same 99.3 EE, what we have observed earlier in the step. So just to summarize today's the presentation, what we have seen here is, so before, so the whole work takes about 2 weeks. The first week is about the first 96-well screening, and after what we have seen, we quickly ordered the 3 other amino indinols and set up the second plate. The second week, we have done the more focused screening, what you have seen. So the overall work took about 2 weeks. So before we went on this collaboration, what we have seen here is because of the poor chiral resolution they have seen in their lab, what need to be done to get enough of these materials is through making this ester followed by chiral supercritical fluid separation and hydrolysis to get enough of this +2. And after this work, they're fully on their way to utilize this condition to separate to get the desired +2. Because we have fairly good yield and the EE is still EE is really good. So what we have seen so far is using our reaction screening system. In this case, is just an experiment, resolution experiment. With this 2-round of screening, what we have seen is we identified optimal condition to achieve this very good mass recovery and very good EE, and also confirm this 2-to-1 salt ratio observed at MMV. And because of what we have seen, and the result within the scale-up is even better than the screening we have done. That will conclude my today's talk.
Thank you, Pu. We will now have a brief question and answer session. If you wish to submit a question, use the Q&A menu on the right-hand side of your audience console. In the Q&A window, you'll type in your question and press the submit button. Assisting me today is Dipsha Angris, who is assisting me with and will read the first question.
First question we have today for Dr. Pu Sun is, how did you analyze all the HPLC data from your screenings?
So, because typically when you do a benchtop experiment, you just run one LC analysis. Because we have typically for high throughput screening, we have definitely a lot of data coming in. So within Freeslate, what we do have here is a central database. So all the HPLC analysis done, I have stated overnight, is saved into this central database, and we have analytical tools to pull out the relevant data and do the analysis, and so we can really highlight the hit. In this case, we have seen where the hits are, and then which will guide us for the follow-up screen.
Okay, thank you. The next question is, how important was a high-throughput approach in identifying this result? Would you have found it using traditional means?
So typically, if you do this traditional approach, if you do it sequentially, sometimes the hint we're getting, which you have seen earlier, is sometimes it's really, when you do a high throughput approach, because you have done all the experiment under a fairly controlled environment in one day with the help of this instrument, you really there's definitely a reduced amount of human error you might introduce, and human variabilities as well. So it's much easier to pinpoint any hit you have seen. If we have done this traditionally, it's really hard to say we'll never find it. It might be just much harder to get to where we need to go that quickly. People, a lot of times, for example, the hint from our first plate, the assay is really just one out of 96 conditions that it was promising enough. If you have done that through a human effort, a lot of time, when do you just give up that particular route? You might give up long before you hit this single clarity, for example. And so the answer to that, I would say, is it's possible, but the high throughput approach gives you much quicker access to a lot of data that manual approach will just much harder to come by. Thank you.
Okay, the next question is, if you were doing a follow-up plate, what conditions would you use if you wanted to further optimize the conditions?
So for this particular screening, what we have seen so far is, for the first, I would say the key take-home message for this particular study is the solvent system had this dramatic impact on the solubility of this 2-diastereomeric salt. So in this particular case, our hit condition, propylnitrile and the heptane 1-to-1 mixture was picked out of many different heptane mixture for the second plate. And just by chance, this solvent mixture was so good in terms of separating the solubility of this 2 salt. And the MMV scientists was so happy with this result, so they're saying we don't really need to further study this. But in case, if for another study, maybe the result you're getting is really not the greatest, there's a lot of things we could have further studied is the different nitrile, for example, acetylnitrile and benzonitrile, and mixed with different nonpolar solvents to further study and the solvent ratio as well. For example, propylnitrile heptane mixture now we're doing is 1-to-1 mixture, but we definitely can vary the solvent ratio of this 2 solvent to see if there's any impact in terms of solubility of this 2 salt. And high-throughput approach is definitely really, with the instrument's help, is definitely the best to do this because they can easily change in terms of solvent gradient. You can go from 10% to 90, 100% sequentially. Manually, sometimes it's hard to do that correctly, say, out of 3 chemists. But here in the instrument, it's just a fairly routine work to deliver that solvent gradient. So the answer to that question is if the result has not been this dramatic, there definitely further study can be done in terms of changing to different solvent ratios and different nitriles at least to further optimize this condition. Yep.
Thank you. The next question is, are your samples processed before HPLC analysis to remove the UV signal associated with the amino indinol?
Let me, no, the sample is pretty much directly from the, like what I will see here is, let me show you the HPLC. Let me push this out. Here we go. So what we do see here, okay. So first of all, the answer to the question is no. We did not need to. So that's actually a fairly general question. A lot of times what we see here with this chiral resolution is you introduce counterion, and the counterion has UV absorption as well under certain wavelengths. And the way typically, so the way typically we have done here is we want to choose a wavelength that is more unique to this compound, and so the amino alcohol itself is not really seen with this particular UV wavelength, and if that's not possible because sometimes they're actually overlapping. In this particular case, we didn't really encounter this problem. But for some other instance, one way done chiral resolution is the key counterion has really good UV absorption. And the way we did it is we still did not treat the sample. So you will still have that counterion in the analysis itself, but we will modify the condition somewhat to separate that particular peak. So that is only done if we kind of have a hint of the good separation with that particular counterion. But in this case, the sample is not treated to get rid of this amino alcohol because it was not interfering with our analysis. Yep.
Thank you. The next question is, why did you choose chiral amino alcohols as resolving agent?
So typically, if we do a study, that is we really don't know a lot about this particular compound, we will actually screen a wide range of chiral amines. But in this particular case, in a way I've stated earlier, is more a focused study, because what they have seen with Rutgers University and MMV is amino alcohol is actually promising. So in this case, is actually directly going to a focus screening, only focus on the amino alcohol itself. That's why we choose chiral amino alcohols. In this, if the story turned out to be a different way, all the amino alcohol we screened was really not that great, another potential further screening is then we broaden our choice of chiral amines to see if there's any other, for example, chiral alkaloids that will help with the resolution. But in this case, because we do have the focus screening and we did get hit out of it, so the study would never veer toward that direction. The storyline is pretty much focus screening. We got hit, the initial hit. We did another follow-up screening, and the result was really good. Yep.
Thank you. In consideration of the time, the last question for today is, why does the EE improve when you scale up?
Okay, so pretty much I have stayed at the end of the second part of the talk is because what we studied is we studied what we have seen in A5. So we didn't really use exactly the same condition as A5 because A5, as we have stated earlier, really did not have enough. 500 microliters of this solvent mixture was not enough to dissolve all the -2 into the solution. So during the real study, scale up, we employ more than enough. Instead of 300 mils of minimum amount of solvent, 500 mil was used to ensure all the -2 has been dissolved. -2 salt has been dissolved. That's why, so the answer is not identical condition was used for the scale up, and we learn from what we have seen during the screening. So scale up is different, and the resulting resolution was much better. Yep.
Thank you, Pooh. That's all the questions we have for today. If you're still submitting a question, we'll keep the webinar website open for a few more minutes to allow you time to send it. Unanswered questions will be answered privately in a follow-up email message by Pooh. I'd like to invite you to visit www.freeslate.com to see our other previously recorded webinars on the application of Freeslate's high-throughput research solutions. To see our previously recorded webinars, select Technical Resources from the upper navigation menu, then select Learning Center from the drop-down menu. This concludes today's webinar. On behalf of Pooh, Dipshika, and myself, I thank you for attending, and we look forward to seeing you at future events. Have a pleasant day.